Hi everyone, welcome to CS188 section 11, and today we'll be talking about neural networks. So we're going to talk about a lot today, so here's an agenda. So first, we're going to talk about the neural network model. How is it written and how is it set up? Now the model has a bunch of parameters, so then we're going to talk about how to solve for the parameters, the unknowns. And this is called gradient descent. And to do gradient descent, you need to be able to get gradients. So how to calculate gradients. And this algorithm for neural networks is called backpropagation, or for short, backprop. Okay, so first let's start off with the model. So a neural network we can draw it as kind of like a flow chart. So we have inputs X, and we perform some operation on them, which I'll draw as the arrow, and maybe we'll apply another function box to it, and then we'll do something else to it and draw another box. Then at some point we get some output y hat. So I haven't filled in anything, but this is how the flowchart is going to go. Now, remember what we're doing. So this is going to be the same thing as perceptrons. So our task is supervised learning. Where we have a bunch of data points X with labels Y. So for example, we saw this in Perceptron. We might have a bunch of pluses, and we'll have a bunch of minuses. So those are the labels, and you want to be able to learn a model such that if I give you question mark, you either assign it a plus or a minus, and we want to do that as best as possible. So before, when we were doing perceptrons, we were finding linear boundaries in the features. So perceptrons, the boundaries are linear in features space. Now, this was pretty good, but we ran into some issues. So for example, if we want to use perceptrons and the features looked like this with all the pluses on the outside and all the minuses on the inside, and remember these are the features, we couldn't find a linear separator. A good separator that's not linear that would work would be a circle. But perceptrons can't do this. So this is motivation for nonlinear boundaries. And this is where neural networks comes in. Okay, cool. So now that we know why we're doing neural networks in the first place, let's go back to our model. So we have some input X, and we want to output what label is it? Y hat. That's our estimate. So in the neural network model, we'll have multiple layers, and each layer, or here's an example of one layer. So that's a layer, and this is also a layer. And what do you do on each layer? So on each layer, on the arrow, you multiply the incoming data by a weight. For example, W1, and then you apply a function to that data, or to the output of after multiplying W1, you apply function G1, and you repeat this. Then you multiply whatever is output by W2, and you put it through this function G2, and then this is for 2 layers, and then the output would be Y hat. So we can write this as a function. So what is Y hat? Well, first we take x1, and in general, we take x, our data. In general, it can be a vector. So if it's a vector, then we multiply it by matrix W1, and then we apply this function G1, which operates on each entry of the vector W1x. And then we do this again. Now we multiply the output by W2, and then we pass it through the function G2. So this is what Y hat is. So let me write out, and then we have the weights, Wi. These are weight matrices. And we have Gi, which are called activations. So the weight matrices, these are unknown. We need to solve for these. So that'll motivate the next one. But the G, their activation functions, these are known. And these are actually really important. So why are these important? So let's say we didn't have any G functions. Let's say all my G's were equal to 1. So they're just identity. Then this means that Y hat equals W2 W1x. Now notice that this is linear. So what kind of boundaries can we represent? Linear, which is not good because that's what perceptrons can do. So we've gained no power by writing this neural net. So what do we want? We want G to be nonlinear. And there's multiple examples. So this is an engineering decision that you have to make. What kind of nonlinearities do you want to do? So there's multiple, but a common one, for example, is called the sigmoid. So it's G of Z equals 1 over 1 plus e to the minus z. And what does the function look like? Well, it's between -1 and 1, and it looks kind of like an S. So that's an example of a activation function, G. Okay, so we have this input to the output, and what's our goal? So what we want to do is that given some data point x comma y, we want our estimate from the neural net, y hat, to equal the true label, y. And if you remember, this is similar to, if you go back to the perceptron algorithm, this is kind of what the perceptron algorithm was trying to do. But we're going to do something slightly different. So if you remember from last week's worksheet, we weren't able to do a neural network that had this loss function. So let me go into how we're going to solve for the weights W, because in the perceptron algorithm we had a weight update. We did something like W equals W plus F or minus F, it depended. But for neural nets, we're going to do a loss function. And it's going to encode this information, but be a slightly nicer. And we'll get into what nicer means later. So for example, an example of a loss function. So I'll write it as loss of the true label and the estimated label could be something like this: 1/2 y minus y, or y hat minus y squared. So this is like the Euclidean distance between the two. So you can see that when y hat equals y, this is 0, so this is small. So when y hat equals y, my loss equals 0. So that's good, that's a small loss. Then let's say y hat does not equal y, then the loss is greater, something bigger. So as we minimize the loss, we're making y hat more similar to y. So I can actually add this into my block diagram. So we have this output y, and it goes into a loss block. And it's also going to take in the true label y, and it outputs the loss. So this is the neural network model. It goes from x to y hat. We have unknowns. This is important. We don't know what W1 and W2 are, but let's say we know them and they're good. So if they're good, then that means y hat and y are similar, which means their loss is small. Okay, so now we kind of define the neural network model. Now we're going to talk about how to solve for these parameters. So what parameters do we want to solve for? So our parameters, at least in the neural network I drew before, they were W1 and W2. These were unknown. So how am I going to solve for these? I'm going to do something called gradient descent. So this is a slight detour. So let's say we have some function. So I'm just going to draw it. And x is on the x-axis, and the function is f on the y-axis. And let's say it's something simple, something like a parabola shaped. Now, the goal of gradient descent is to get to the bottom of the function. So I want to end up at the lowest point, which is right here. But let's say I start somewhere else. Let's say I start right here. Now, the question we want to ask ourselves is, where should I go? So what you can actually do is, you can imagine that this parabola is actually like a valley. And you're somewhere up high on the valley, you're where this dot is, and it's a hill, and you want to know where should you go. So you should go downhill. Now, what does downhill mean? So this is going to have to do with derivatives, because derivatives tell you the slope. So if I take the derivative at this dot, it's going to be the tangent line, and it's going to be something like that. Now, so that's going to be df dx. But remember, the derivative points in the up direction, and we want to go down. So we want to go in the negative derivative direction. So I can be at this point, I can find my derivative, and I can move along this point. So I can move from here, and I take a step in the negative derivative, and I end up here. Then I can find the slope here, and I can do it again. And I can continue walking along the derivative and recalculating it until I reach the bottom. So this gives us an iterative algorithm. So it says update my x to be my current x, and I want to move in the negative derivative direction, and I'm going to have some step size. So alpha is how big a step to take, and this is known as the learning rate. So let's think of this learning rate parameter. How does it affect going down? So let's say alpha is small. So this will lead to small steps, which is slow because I'll have to do many updates. So I'm taking tiny steps, but I'll be walking in the right direction. I'll be going down the slope correctly. Now, when alpha is big, you'll get big steps. So this is faster, but you might walk in the wrong direction. So this is a hyperparameter that you'll have to tune. And there's many algorithms that talk about how to choose the correct alpha, which we're not going to get into. Okay, so this is in the 1D case, but in general for us, what we're going to have is we have our graph, and our parameters are the weights W, and what we want to minimize is our loss. Now before, when I drew up here, it was easy to find the bottom because there's only one local minimum. So this was nice because this was convex. That's what having one local minimum means. You can think of it as being bowl-shaped. But in general, neural nets are complicated and they're nonlinear, so the loss function could look something like this. So it could have a bunch of these minimum, and only one of them is the best one. So for example, let's say I start here, and if I do gradient descent with small steps, I'll end up at the global minimum, which is good. But let's say I start here. Where am I going to end up? Well, I'm going to end up at this x, which is a local minimum. So it's global and local. But what we're going to say is that local minima are good enough for what we want to do. Okay, so for a neural net, how are we going to update these weights each iteration as we walk down our slope? So we want to update our weight W to be the current weight minus the learning rate times the gradient of the loss with respect to W. Okay, so now that we've done gradient descent, the big question is how do we calculate this term, the gradient? So this brings us to the algorithm of back propagation. So let's draw our neural network model again. So we had x, and then we multiply by W1, put it through G1, then we multiply by W2, put it through G2, and then we put it into our loss function. Now came our loss, and this is y hat, and this is y. So to be able to do gradient descent, we need to calculate the derivative of the loss with respect to weight 1, because this is unknown, and the derivative of the loss with respect to weight 2, which is right here. So first, what we're going to do is we're going to do forward propagation. So in forward propagation, we start with input x, and we're going to push it forward through our neural network, doing these calculations. And how we're going to do it is we're going to define a bunch of intermediate values. So right before we apply G1, we'll define a variable called Z1, and right after G1, we'll call a variable A1. And we'll do the same thing for the next layer, Z2 and A2. So let's write out what all these intermediate values are going to be. So Z1 equals W1 times X, A1 equals G1 of Z1, Z2 equals W2A1, and A2 equals W2, and A2 equals G2 of Z2. Note that y hat is actually the same as A2. And then our loss function A2 comma y, we're going to do this loss function. I'm just choosing this as a design. There are other loss functions. So this is forward propagation. So what I would do is I would go through and I'd find out what Z1, A1, Z2, and A2 are. Then we do back propagation to calculate the gradients that we want, which are up here. And this is, back propagation is just a specific algorithm for applying the chain rule. So first we're going to do dloss dw2. Now first I'm just going to write out what the chain rule is for this, and then I'll explain why we go and do this. So we can write dloss, and as doing back propagation, we're going to work backwards. So that's what the motivation is. So what is my loss function in terms of? It's in terms of A2. Now what is A2 defined as? A2 is defined in terms of Z2. And what is Z2 defined in terms of? W2. So first let's ignore where these came from and check that this is a valid use of the chain rule. So this is Leibniz notation, so you can kind of just do dimensional analysis to check that it works out. So A2 and A2 are on top and bottom, so they cancel. Z2 and Z2 are on top and bottom, so they cancel. So the right side ends up being dloss dw2. So this is a valid expression. But now what we need to be able to do is to calculate each of these little parts, these gradients. So the way that we applied this chain rule was by looking at these equations, we wrote in forward propagation and working backwards. So my loss was in terms of A2, so I did that. Then I looked at what was A2 defined as, well, it was defined in terms of Z2, and Z2 was defined in terms of W2. So that's why it's working backwards, that's why it's back propagation. So now let's actually calculate all these values. What is dloss dA2? Well, if I look at my loss, it's just going to be A2 minus Y. What is dA2 dZ2? Well, I would be given my function G2, my activation, so it's just G2 prime of Z2. And what's dZ2 dW2? Well, this is just A1. So this is how you would apply the chain rule to do dloss dw2. And then you could go on and do dloss dw1, and it'd be a very similar process. So what we can do is go back to where we started. And we have the model. We talked about gradient descent, which is how to solve, given a loss function, how do we find the bottom of it, the minimum. And to do gradient descent, you need to calculate gradients, and we talked about how to do backprop.